Hi, everybody. So great to be back at the Ezra seminar and see that there's food. I think when we first came back, it was seminar but no food, right? So now we're moving back. I'm Lindsay Anderson from Biological Environmental Engineering and from Systems Engineering, and I'm really excited to introduce Michael Charles today because he is a new faculty member in my home department, Biological Environmental Engineering. So Michael actually did his undergrad at Cornell in chemical engineering before he went off to the Ohio State University for his graduate work. He did an MS and a PhD there, also in chemical engineering, right?
Yep.
And then we were lucky enough at Cornell to scoop him back as a new faculty member. Right now he's a Provost Excellence Fellow. I think that's the name of it, right? Sorry, I should have checked before I came. But he's starting his tenure track position July 1st in our department, so we're super excited to have him back. You can read the title of what he's going to talk about today. But basically, and I also want to mention that in addition to being an assistant professor in biological and environmental engineering, he's also affiliated with the Indigenous Peoples Program, American Indian Indigenous Studies Program at Cornell. His research interests are in sustainable system design and optimization. A lot of people do these kinds of things, but one of the awesome things that Michael brings to this is the way he incorporates community and stakeholder engagement in making those kind of design decisions and including them in models and so on. So that's not only unique, but also really, really important if we want to make the right decisions that actually have positive impact. So that's excellent. What else do I want to say? Michael's a member of the Navajo Nation and represents the interests and rights of the indigenous people within the UN climate negotiations as a member of the International Indigenous Peoples Forum on Climate Change as well. So in addition to his academic work, he's also got a really nice reach globally into understanding sort of what are the problems that we need to solve and what are the different perspectives that we need to take into account to solve them. So I know you have lots to tell us today, so I'm going to stop there. But let's have a warm welcome for Michael Charles. I think so. I'm looking at Oliver. It goes to 1:30, right?
Yes. Okay, just making sure. All right. Thank you so much for the introduction, Lindsay. Yeah, I'm going to go ahead and get started. So we'll be talking today about just generally how do we expand systems engineering to include things like people on the planet, as seen in the title. So I'm going to actually start today by just going with a quote. There's going to be 3 of them. I know it might be a little cheesy, but just bear with me. There's a reason for it. So I'm going to start with this, which is, engineering is the art of directing the great sources of power and nature for the use and convenience of man. And this is by a man named Thomas Treadgold, who was an English engineer and an author, known for early railroad construction. This is also the concept in the kind of the motto that founded the Institution of Civil Engineers. And if you don't know the history of engineering, it really started as a military science where engineering was all about developing military engines. And then the next thing that spanned off of it was civil engineering. So in some ways you can kind of think of civil engineering also as kind of the representative of engineering as a whole at the time. And the reason why I bring this quote to you today is to just begin by talking about the development of engineering and how it focuses on benefits to us as humans. And it was developed in this anthropocentric worldview, meaning that the world revolves just around us humans. When we think in this paradigm, that means that everything on this planet is a resource for us to use and can be treated as ours to take. So this is important to note because it creates a separation between humans and nature, and it creates this kind of us versus them mentality. Even how we define civilization is not revolved around people and the connections we make within a society. It's based around our domination and transformation of land. It's based on how we control or own it. And so for an example, we wouldn't really commonly think that someone or a group of people who just choose to sleep outside on warm summer nights is as civilized as those who own land and have purchased a house, unless it's like a hobby with fancy gear purchased from REI. But this outlook just views nature as a source for our resources and a sink for our waste. It creates a relationship between us and nature that lacks reciprocity. It's a relationship that ignores the livelihood of the planet around us. And to no surprise, this development of industrialization has come at a price. We're experiencing the impacts of our uncontrolled scale of activity and resource extraction through environmental degradation and climate changes. And as a result, we're now living in what's known as the Anthropocene, which describes this time of the Earth's history in which human activity is actually beginning to have a significant impact on the planet's climate and ecosystems. So our anthropocentric worldview is undoubtedly connected to the environmental and climate impacts that we're currently experiencing, and also those that are to come. However, we know that technological advancement has also played a positive role in society, and I'm not here to undervalue the economic growth that engineering has played, and the role that it has played in that economic growth, or the changes in livelihood that we experience through increased access to information, health, food, necessary products, even warmth as a result. The warmth seems particularly relevant today. And I'm here just to encourage a reframing of engineering, or how we approach and bring more attention to the ecological knowledge that we seem to really have lost. Studies have shown that countries with higher education and technological deployment have higher GDPs, or gross domestic products, which is not necessarily surprising. And even furthers, the countries with more money and more economic growth are also those that are recently investing more of these resources into environmental conservation as a response mostly to the damages we've caused. But there's also these other studies that really focus on the result of economic growth and the impacts on ecological literacy. And what they found is it's actually negatively correlated. So the more and more that countries become wealthier or grow in their economic metrics, the less and less they're able to identify the plants around them in what we call ecological literacy. Which means that the development of our civilization has also just separated us further and further from the land that we walk on every day, we rely on for food, we rely on for clean air, for clean water, and all the other gifts it gives us. But it also tells us that those countries who are able to invest the most in environmental conservation are also those who have the least social capacity and knowledge to even manage our environment. So I'm going to the second quote, in which we cannot solve our problems with the same thinking we used when we create them. I will bypass the history lesson because I'm sure we're all familiar with Albert Einstein, but it is a very important quote in the idea of, if we're going to solve these problems, we must really change the way we think. And so this is kind of the work that I do, in which we talk about how ecology and engineering have been separated through the development and for far too long. And so how can we address that lack of ecological literacy and the exclusion of nature? As system engineers, we can think about it in a way as we're expanding our system boundaries. We change the way we think to solve the problems in a different mindset than when we created them. So this figure on the right kind of explains how we can expand from only focusing on technological systems, or what's in that kind of dotted dash black box, to including ecological and social systems. We can see how these systems connect with both positive and negative impacts on each other. These are just kind of some examples that I put together, but in general, we have these technological systems because we're trying to create some sort of product. We have already ecological inputs that go into our ecological systems, the energy that comes from the sun, from the waves and things like that are constantly generating some of our resources and the materials that we already have here on the planet. And we know how our technological systems use those raw materials. They also, to create the products, they also have impacts on our social systems, right? So it can be negative health impacts, but it could also be positive impacts that we've talked about on our livelihood. We know that ecological systems and social systems interact in the way that we rely on nature for a lot of ecosystem services when we go enjoy the aesthetic of a landscape, when we go hike a mountain, when we eat food every day. And there's also ways that we can give back and create this more reciprocal relationship as a social system in which we're actually putting inputs back into the land. We're investing in the land, we're respecting the land, we're either we are making decisions on how we use the land, we're managing it. And then there's also these, kind of going back to the technological system, ecological system, the environmental impacts we see from technology, which we see as a kind of a negative impact, but also some of the impacts we've used for technology to impact the way that we grow food, or examples like agrotechnology. So these systems that are all constantly interacting with each other. And I think the expanded system boundary embraces more opportunities. So you think about when we're only designing a technological system, we're limited to the variables that we are more familiar with in terms of anything we can put within the box that we want to control. But as we think about these expanded systems, we have a lot more opportunities or variables for addressing issues like sustainability and the other grand challenges that are specifically posted in like the UN Sustainable Development Goals, which include poverty, hunger, health, clean water, affordable energy, just to name a few. However, we also recognize that expanding these system boundaries also invites just as many challenges as opportunities, if not more. So a lot of my the work I've worked on at Ohio State and parts that I still continue to do really focuses just on the techno-ecological system. And so a lot of our previous work has shown that we can find these win-win solutions where we find cheaper solutions that provide more sustainable options depending on the metrics we're looking at, but mostly just gives hope and promises of the role land and ecosystems can play in our attempt to kind of pursue sustainable solutions. We've developed frameworks. One that we've kind of used the most within that lab was a framework called techno-ecological synergy. And this has been applied to many systems and scales. We've done projects or case studies on households, manufacturing sites, regional planning. So the question that I'm kind of trying to pose with work going forward, and really as we talk about people and the planet, is this idea of how do we include social systems meaningfully? I realize that one of these two computers will time out if I don't give attention to both of them. So I'm on to the third and final quote, I promise. And that's that all models are wrong and some are useful. And so as a computational lab, I think this is extremely important to know that everything we create is inherently wrong. But we're really just trying to search what's useful, what brings more insight, what can help bring new questions, bring new answers. And so, yeah, there's a little history lesson, but I don't think it's actually that important. So we're going to skip that one. Essentially, George Box is an older person. We'll go with that. So this leads to the overview of the work that I do, the work of the lab that we're building, in which we are driven really by three guiding questions. The first is, can we tell stories that need to be heard using data? Can our work in a computer lab provide new insights to decision makers who are deciding how to invest resources and implement responses to sustainability issues? And then finally, can we create computational approaches that are useful to community members and adapt to their feedback and local needs? So this is just kind of a list of some examples of the projects I've worked on, either currently or in the past, and how they might relate to these kind of three buckets of work. That's the analogy I'm going to pull from. And so ideally, each of my projects drip a little bit into each bucket, as I believe compelling research should provide novel approaches that's delivered in a compelling story to academics, decision makers, and communities to instigate new ways of knowing, being, and acting. So today we're only going to talk about two of them because there's not going to be enough time to just sit and talk through all of them. We'll focus today on long-term planning for carbon neutrality and how do we inform these solutions through spatially explicit methods. So talking really about the dynamics of time and space in industrial landscapes. But just wanted to kind of also just show some of the other stuff we work on, or I have worked on in the past, which is being able to tell stories with data. So example is how land-grant universities impact indigenous food sovereignty. So inherently, land-grant universities are founded based on the selling and taking of land. So connecting that to indigenous peoples, today's reservations, and looking at impact on indigenous food security. We've done work with analyzing the sustainability of small-scale and urban agriculture, so getting to work with small-scale farms out in Ohio when I was at Ohio State, and getting to tell the story of why they do what they do. We also have ecological network analysis and topological network design. which is essentially how are things connected? Are there redundancies? Do we meet the demands we're imposing? Are our systems reliable? But more importantly, how do we impose that on space and in real world problems that have topological impacts, geographic impacts, and so making them really more tailored to real world problems. And then finally one around hierarchical design for computers and communities. And so people in process systems engineering are usually familiar with this kind of hierarchical process design procedure that we go through, in which initially was, I think, really towards chemical engineering, but it was, level 1, is it batch or continuous? Level 2, how do we design the reactor? Then how do we do the heat exchangers? Things like that. There's levels through it. And so I presented maybe 2 years ago at the American Institute for Chemical Engineers about a proposal for just more of a conceptual framework for including ecology into that type of hierarchical design. So that's something I'm really looking forward to with community partners in the future, is how do we take community feedback and really change our models, and can we kind of find a systematic approach for that? So that's just kind of the bucket, so we'll go ahead and start with the first project, which will be the long-term planning for carbon neutrality. And so this is motivated by the same contract that Ohio State signed, that Cornell has signed, and that's the American College and President's Climate Leadership Commitment, or the ACCC, which was founded in 2006. Currently, we're at about 400 institutions that are committed to achieve carbon neutrality, and specifically with a target date. Cornell's is 2035, if you're not aware. And so we worked on the Ohio State Climate Action Plan for a few years before we even came to a research project. And some of the things we really learned while working with this team that included, the facilities managers, the higher administration, people in business and those controlling the finances, and then researchers, and even outside parties and consultants, which was a very interesting, what I would call a conflict of interest, but we'll let that one go. But the observations we got from developing this type of kind of multi-party, multi-stakeholder work was that the number one thing was land-based carbon sequestration was really often ignored, or at least not quantified by institutions that were reporting these climate action plans. And the second was that decision-making was extremely limited by, first, the availability of information to even just compare multiple options at once, and two, uncertainty about the future. So we had this objective, this idea, how do we create a tool that just generates scenarios for achieving neutrality, optimizing for the lowest cost pathway, but including ecological solutions, and ideally being adaptable so that any institution could use it. So that led to our development of a tool we called Decarb, or Designing Climate Action and Regulations for Sustainability. Since this is systems engineering, I tried to bring the systems approach. But ideally, and the figure tells the same story as the math framework, in which case we're trying to develop these modules that could include technological and market responses, it could include behavioral responses, it could include ecological responses. And each of these modules we developed to include the cost, the emissions, the utility, so if it provides something like electricity or heat, what's the utility that we're using, technological lifespans, temporal dynamics. For instance, solar is going to have a different capacity in the summer than the winter. Wind, the same thing. Trees are going to have this long-term dynamic of ecological growth. So how do we include all of these types of things? So each of these we package as a module, and we put it together in one program that essentially, for this case, had an objective of let's minimize the cost so that we achieve neutrality. And so all the math on the right is essentially telling that same story, in which here we're minimizing the cost of both the technological and ecological responses such that the emissions achieve neutrality, or the emissions are less than 0 at our target date. We're making sure that our utilities are met, so if we have a demand for electricity, we're making sure that we provide whatever is demanded by the community. We're making sure that these two kind of talk about the capacity of technological systems, so as we invest in capital projects, we're making sure that we operate it within those capacities of we can't operate a 200 megawatt solar plant at 400 megawatts. So very, very obvious physical limitations, but it has to be included in the math. We're making sure that all of our ecological projects or land restoration and land use is done within the physical constraints of land available, and making sure that in the time sequence, since we do include space and time, or this one's just time, making sure that we're not also just saying, oh, we replanted the same area of land over and over and over again, so that's another physical constraint. And the idea is we can turn these modules with all these different variables and put them in the forms of basically two matrices, one which is a technological matrix and one that's an ecological matrix. If you're interested in this, besides just asking questions at the end, there's also, that is a published paper that just came out last year. So if you're interested in more of the methodology. But what was interesting at Ohio State was the opportunities there was with just the land area that they had. They had these different regional campuses. In a lot of ways, Cornell parallels that with the amount of land that we have in different spots across the state of New York. And so we found that, you know, a Columbus campus, which was the biggest operation, it's one of the biggest schools in the country, wasn't necessarily where we saw the most potential for planting trees. But what's interesting about the carbon problem is it's not necessarily where you plant the trees that makes it interesting, it's just how much carbon sequestration can we get out of it. You consider that more of just this global service shed of, doesn't really matter where you're taking it up from, you're benefiting that the atmosphere and the overall global carbon concentrations. And so these were just some analysis that we did. We used a tool called the iTree Eco, which is based on the U4C carbon model, and we were able to have this data set of about 11,000 trees. So we're putting in the species, the diameter of every tree that exists on campus, and we're projecting what already exists. So that's in the red bars. That's kind of the current sequestration. But then we looked at what happens if we just change the management of that land. So are there methods of practical methods for just changing how we manage to really focus on improving the carbon sequestration rates? And then we also looked at what if we were to implement land use changes. So what if we were able to change grasslands to trees and tree stands? And so that's kind of the difference between the gray and the greens here. The dots kind of show how it compares to the actual emissions of each campus. And what was interesting is all of the rural campuses aren't as big, so a lot less activity, a lot more sequestration potential, and in some cases actually pretty even to what we had at Columbus campus. But in terms of potentially achieving that carbon neutrality on their own just by land-based methods, 4 out of the 6 campuses were able to do it from these, best case potential scenarios. So just really showed the value that land could have. This also includes temporal dynamics, but we'll talk about it actually in the second project because it's going to be the same model. And so the results of this tool is essentially being able to map out what are we doing each season between now and the next 50 years? How do we optimize this transition? So this includes a lot of assumptions I'm not really going to go over because we won't have a ton of time to do that. But essentially, what if we have budget constraints? That's why you kind of see these slow transitions between bigger investments into these combined heat and power plants, so different places and different chunks of where we're actually investing. And then we see those slower transitions away from the grid or reliance on wind, and then also including solar. So the light lines are all the seasonal dynamics based on just kind of, I think we had like 10 years of their past data. And then addressing both electricity and heat. One thing we did learn was there really is this reliance on offsets because they hadn't really discussed a basically renewable heat source for how do we address heating up the campus. It was basically we're either going to have our conventional boilers or we'll rely on our CHP, both which use natural gas. So there really wasn't there wasn't really a possible way to hit this neutrality goal without really a reliance on offsets, which kind of will lead to the motivation of the next project. But it was just a kind of interesting tool that we could use just to generate these pathways, generate scenarios. And I won't really talk too much about the actual production, but...
So Michael,
yeah.
With that, so the last graph at the bottom right, is that the objective function? The value of the objective function?
Yeah, so the value would just be the area under, because it's the total, but yeah, it's minimizing the annual cost to basically meet the carbon neutrality goals, but also all of the different costs of each module included. Yep.
Since Oliver already interrupted your flow, just a quick question. Am I correct in interpreting that plot on the top left that what you're seeing is an investment in basically a CHP that you then run for 25 years and phase out?
Yeah.
Okay.
Yeah, so essentially, and that what was interesting about this is that was actually what they were already going to do no matter what.
Right.
That was one of the third parties that was part of this plan, was the people selling the CHP. But it was something we did warn them about, was you're going to be locking in this technology that's inherently relying on natural gas.
Yeah.
And so their plan was to get, all of the metrics they had for carbon savings and how much money they were saved was basically relying on it being most of the production for the entire campus for 20 to 30 years. So we kind of showed that if you want to reach your neutrality goals, that's an option, but you're also, there's also other ways to do it, right? We could also minimize emissions as well as cost, and the CHP would go down pretty quickly, or not even be built at all. So that was essentially what it was, is we'll just hold off on putting any really renewable. They already had a contract of wind, so that's why it's actually constrained to be there, is because it's contractually there at the bottom. But then it was like, let's just wait till 2050, put in the renewables, and that was kind of it's kind of an expected thing if you're only going to minimize cost. But there were other things we looked at of, let's put a 50% emissions reduction by 2030, then what happens? And you'll see the CHP kind of cuts off a lot lower. But what was great about this tool is that we actually could just run all of these scenarios, these things solved in like less than 2 minutes, if not like shorter than that. This one might have been only 10 seconds. But we were able to implement, what if our neutrality goes by 2030, 2035, 2040, 2050? And that's where you kind of see this trade-off, right, between costs and cumulative emissions. And then what if we included more budgets? So the one we showed is actually the budget scenario where it was a cap on how much you could spend each year, just a little bit adjusted over their already operating budget. What if we didn't even assume neutrality and we only ran the electric grid and the conventional boiler? How does that cost compare versus the emissions? So you see that even the neutrality by 2050 still gave us cost improvements. And then what if we just relied on the grid boiler and purchase market-based offsets for achieving neutrality? The most expensive option. I would not advise any institution to rely on that. But a few things we learned is that obviously the first one is that the trade-offs do exist. You're going to have this trade-off between your privatized costs and also your cumulative emissions as we're looking at these transitions towards carbon neutrality. And then the more and more we implement budgets, which is the more and more we kind of go away from the best solution if we had all the money in the world, it's going to push it off what you could call the Pareto. So kind of what is that Pareto curve, or the optimal trade-off between costs and emissions, and the more and more we implement budgets and budget scenarios, the more it's going to push it away from optimal. And then one other thing we talked about was the role of uncertainty. And this one's just kind of interesting because how do we address uncertainty in something like the offset price? We have no idea what the price of carbon will be in 2050 when all of these offsets will be implemented. We have ideas, we have projections, but there is deep uncertainty. And so rather than us trying to find a way to include uncertainty in all these values, or even uncertainty in the models, we actually approached, first of all, just recognizing that we understand the uncertainties there, but also just try to do variable sensitivity. So this was, I think, more specifically helpful to decision makers. It wasn't, there's a 30% chance in this range that this will hit this. It was, well, if everything else is close to correct, and we see the offset price of carbon just increasing, at what price do we have to start implementing the land management solutions? At what price of carbon should we really be investing on these energy conservation measures, which are big investment projects? The ones they were considering were completely changing from, I think it was a gas or a vapor to a hot water heating system, and expanding that system. And so those were kind of the projects they looked at, but these were examples of, let's just look at one variable and kind of change that price. So that was something we did. The paper actually shows a few different variables where we do that through as well. But it's good to know that there might not just be an incremental change, but there might be times where there's really a tipping point of a variable of which the entire solution changes, or the choice of technology changes. And that was more what we were looking for than let's just look at this linear trade-off and pick a point that feels right, which would become a very arbitrary exercise. And so we'll kind of talk a little bit just about the challenges and insights of this project before moving on to the next one. And the first, we'll start with the challenges, is that deep uncertainty. It really impacts these results significantly, and that's going to be the same in any future planning problem. It's the same as we're doing on a global level, trying to predict the impacts of climate change in a world where we don't know what's going to happen in the next 50 years within the Earth's systems and Earth's processes, but then we don't know how we're going to react as people. Are we going to take it seriously? Are we going to invest things? Are we going to do it in a good way? Are we going to do it in a wrong way? Are we going to try and fail? Or are we going to succeed in mitigating a lot of climate? So that's, people also put a huge uncertainty into it. We also understand that the module accuracy, the models that we are actually using, is very dependent on what available data you have for the university or for a given case or place. We were lucky for a lot of these to actually have already reports that said, this project will be this many dollars and we estimate this carbon reduction. So another team was looking at that. And so rather than us building a model that says, y equals x to the third minus whatever, it was, if we implement it, this are the trade-offs. So that is the difference between, when you already have people looking at it, and so that module accuracy is highly dependent on what is available. Each module also varies in input data resolution and accuracy. So I gave the example that like solar and the demands we had were done at a seasonal level, but for the trees and the carbon sequestration, we did that at an annual long-term growth scale. So if we do that with other technologies where higher resolution may not give us a new insight, you could introduce potential bias. You also have that behavioral and policy responses require collaboration with social science expertise. We didn't have a lot of behavioral scientists who were really helping, so we didn't actually include any of the behavioral models in this, but we did show in that original framework that would be possible, and hopefully is possible and can be implemented. And then kind of the last one, I guess that's more on the insights. I think that got skipped. But the insights then would be, the first one is like, if we have the money, large initial investments really can lower the overall costs. And one of those big investments that should be focused and highlighted on is land-based approaches. They're often cheaper than technological solutions and market-based offsets, but they do require time. They require time to mature before you're ever going to reap the benefits. So it's one of those things that if we want to take those seriously, the time is now. A diverse set of technologies can be used to counter seasonal intermittency and demands. The tool provides fast solution times. This one does solve in about 10 seconds, including generating all those graphs, which enables us to just explore many of the scenarios. We can look at parameter sensitivity and just see how useful it is. And really, it's the first step in developing something that's more robust, has improved accuracy and relevancy for decision makers, and ideally would have feedback from people deciding, whether it's administration or people in the finance sector, what information do they need to make a decision. So we're going to go ahead and talk about the next project, which is kind of the idea of spatially explicit solutions. And I'll probably try to go a little quick so I make sure we have time for questions. So the first is just this idea that interactions between, this is going to be heavy, but this was the only phrase I've seen published, is the social, ecological, technological systems, which is essentially manufacturing sites and their neighboring communities, or just people and landscapes broadly. But we know that these systems are dynamic and spatially variable. We know that geospatial data is measured or collected, but in some cases, but really they're most likely going to have to be simulated. For ecosystem services, some services do not pose spatially interesting challenges. We just talked about the role of carbon, and one thing I said was it doesn't really matter if we planted it on our main campus or if we planted it out in a rural area, we're still going to get those carbon benefits on a global climate mitigation scale. But if we do include co-benefits, we can create these spatial frameworks for approaching land-based responses. We can get better information on, all right, so where should we do this strategically, not just how much should we do it. So sometimes we can include things, in this project we'll talk mostly about human health, so the impacts of something like particulate matter. So if we do have an industrial system somewhere in the middle of our map, we know that the operation of that system is going to cause pollution, whether it interacts with people, whether it interacts with the ecosystems. How can we include those other co-benefits, such as air quality regulation of the trees or the ecosystems, to create a more spatial framework for how we should approach land-based solutions? And finally, the role people contribute to ecosystem services. It's both the supply and demand, right? Where people live shows how they're demanding. So if it's people within a watershed, the amount of people matters how much water we need from that watershed. If it's even the supply, so for instance, if we're talking about air quality regulation, the ecosystem services are going to provide a lot more value in an area where there's more people who might be exposed to the contaminants, to the pollutants. And so people do contribute the values that we give to ecosystem services. And so we're looking for more of an objective of how do we decide where to put this? How do we decide what this land use should be versus this? If these houses are already here, maybe where do we put the manufacturing site? Or if these houses are here and these ecosystems are here, or this grass could be turned into something else, what should we put there, or where should we? Or we're looking to put 10 trees somewhere. Where do we put that? And so that's kind of what the idea when we're looking at these spatially explicit solutions of social, ecological, technological systems. And I'm sure there's a better way to describe that, and we'll start with that as the next research question. But we'll start with spatial variability, so just talking about space. And so to develop frameworks that utilize spatial data, we must first be able to generate spatial data, and specifically useful data for our purposes. I won't really go into this much because it's mostly just another process. So it's CalPUF modeling system. It's essentially a process or a model to develop spatially explicit concentration and ecosystem service uptake. So this specifically looks at the flux of trees for pollutants like, the case we'll look at is ozone and particulate matter. And so it includes basically spatial land and elevation data. We create a geophysical model where we can implement these different land use changes. From there, we interact it with the meteorological data. And essentially, we're just running this model to determine the meteorological plane of this area. And then we include things like our technological point sources and any background concentrations, and we run this CalPUF transport and deposition model. But the main thing we need to know is we have now spatial concentration and spatial uptake of the trees, or the flux. And so that's space. Now we'll talk about time. And these are also the same temporal dynamics for here in carbon that we use in the Decarb module. But essentially we're using another tool from the US Forest Service, which is the Forest Vegetation Simulator, where we're simulating, this was specifically for Ohio, so we simulated 3 of the most common species for the case study in Ohio, which was sugar maple, white ash, and yellow poplar. We add in our certain parameters, so we're looking from basically introducing a new sapling to maturation with very limited inputs. So just assuming you put it there, maybe do a little bit of watering and things as it's young, and then just kind of hands off. And so what we've learned is we can develop these models for both dry deposition, which is going to be what addresses air quality regulation, so not including the carbon, but thinking about the particulate matter and the SO2, NO2, things like that. That's the dry deposition, and it's related on the tree crown cover. So it's based on the leaf stomata, so it's how many leaves can we get across the surface area, essentially. And then carbon is based on just the rate of change in the carbon both above and below the ground for a given forest stand, and that's where we see that actually young forests start off by emitting carbon. It's the same in agriculture, where it has this process of respiration that's dominant compared to the sequestration. And then we know that with carbon sequestration, eventually these trees do start to stop growing. And that's where we're going to start to hit a peak. But within 60 years, 40 to 60 years, that's kind of the maximum sequestration we're going to get. And then that's going to reach a peak. We don't really know what happens. Some say, well, it'll probably go down to 0. The other thing to think about is when you have a peak like this and a change, that regression is really only valid within the time spot, like the timeline that you've used. So we're looking at a time span of 80 years, and after that, you can't extrapolate this because we don't know what that will look like. So I mentioned that we're looking for a spatial framework so that we know when we plant trees for basically climate responses, we want to get the added benefits. So we're going to actually look at addressing spatial health risk assessments. Sustainable design is inherently linked to human health, but it's also some of the leading causes of death around the world, which is air pollutants like ozone and particulate matter, less than 2.5 microns in diameter, that pose these significant health risks, specifically with respiratory and certain cardiovascular systems. And these health risks have severe spatial impacts that can cause further inequity consequences across various demographics. I talked about using data to tell stories. There's also a very interesting story about the history of where we've redlined zones for industrial use and how that relates to minority communities. And so this is addressing spatial things like that is more than just health, but can also really lead towards kind of a more just and equitable future when we talk about design. We choose to include health impacts through economic valuation of averted or mitigated health risks for two reasons. And this is like why we want to actually turn a health risk into an economic value. The first is it's very consistent metric and unit that makes it easy to include into objective functions. That helps you just solve it as a singular optimization problem instead of a multi-objective program. And then the second is anyone here familiar with the term of like a social cost? We talked about the social cost of carbon. We know there's a social cost of methane. And that's specifically in the context of climate change, where we give a dollar value to what we expect, your emissions to be the cost of society for now having to live with the I guess your decisions is the best framework I can think of at this point. But it's a way. Social costs basically provide us a way to include society and techno-economic analyses. So the way we talk about technology and economics, and in a way that we can include things like the concerns for sustainability or health by putting a price on a certain emission or pollutant. And so in that case, that's more of a let's tax carbon for people who pollute it or emit it, say. But since we're talking about the mitigated costs of basically averted health impacts, or even with climate, we're going to refer to them as social benefits, since it's really just a negative cost. But particularly, we're looking at avoided mortalities associated with exposure to ozone and fine-scale particulate matter, and to connect these health impacts to the spatial information that we simulated, we need to calculate the resulting change of concentration due to the pollutant uptake from the land use changes. And so the first equation of calculating the concentration change from the flux data is essentially just a simple mass balance. We're just assuming that each receptor or area of land we're looking at is essentially a big rectangle up to the mixing height, and then it's just a mass balance, and then we use that percentage change into a health impact function, and this is essentially basically just paired with an epidemiological studies, that's the word I'm looking for, that simulate health impacts due to the concentration changes. So this is actually a huge area of study where lots of papers have talked about the change of concentration for particulate matter, for specifically looking at days in a hospital, or we'll look at mortalities, but there's a lot of different health outcomes that have been looked at. This is kind of the incidences that we're looking at, so this could be days in a hospital, or mortalities is that delta Y. That's what it's known as, it's just the change of incidence. Basically, these two functions are just summed up in text below, and we're looking at our avoided health costs, so our social benefits, and it's just equal to the baseline incidence, so that's the already days we're spending in a hospital in that particular area, multiplied by the health risk estimate of air quality concentration changes, times the exposed population, so again, where social systems play a role in these outcomes, and then finally the value of the avoided incidence. So, what's the value of life is another social cost we've put on that is kind of actually announced by the White House I don't know why, but that's another kind of value that we're putting with an avoided incident. So if it is a mortality, then we're using the value of life. So that's just kind of an example of how we're going to do this. We'll go back to the framework. Didn't actually share the math this time, but it's essentially similar, where we're creating this optimization program looking at costs. Now we're just, like I mentioned, we don't have to do a multi-objective framework because we can include the social benefits within the cost outcome. And then we can also choose to include emissions if we wanted to. That could be separate, or it could just be if there was a specific emissions goal, or it could just be an artifact of including the social benefits. We found that it usually just becomes an artifact of including the social benefits. Then again, we have the technological systems, we have the ecosystems. We're looking at building similar modules as we talked before with cost, capital capacity, pollution removal. But this time with the ecosystems, we're looking at including space and time dynamics, and particularly adding a spatial health risk assessment. So this ends up becoming a mixed integer linear program. People familiar with programming, anytime you really are going to include space as an optimization, as a function within the optimization, is most likely going to require a mixed integer program. We look at two matrices of decision variables, similar to what we did in the Decarb framework. Looking at land use, we use a matrix of binaries where we're really looking at when and where. So we have the matrix, we have it each one for each time step, and we're deciding a one is, that's where that's where and when we're gonna plant something. Technological scalars are just when and how much. We have similar functions and constraints as we did before, and are able to write them all in terms of the decision variables. And then again, we have these features, which the economic features, which include discounting, adding annual budget constraints. And this one takes a little bit more time. It has about 93,000 variables when we look at basically a 41 by 41 spatial grid. I think this was with about 60 time steps. So we looked at operation over 60 years. It takes about 2 minutes. If we've been doing most of our work in Drovi using the programming language Julia, and one of the packages in that Jump. So looking at results, the first thing is that we have basically set carbon neutrality as the target and the goal, so that's maintained throughout. You'll see that in the top left, that net carbon is essentially that black line. But then around year 25, we actually see the use of the technology goes off to 0, and we actually then at that point we still get ecological benefits, and we start seeing that become what we would call a carbon positive or a net positive operation. And I will note that this is for a very large scale project, so it is one manufacturing site working within basically this multiple counties, essentially, in terms of restoration projects. And then we look at the climate and health benefits. Over time, what's interesting is the value of basically the uptake of one ton of particulate matter is actually worth a lot more than 1 ton of carbon. The impacts that lower concentrations have on health is actually deemed a lot more valuable. And so, but it's limited by trees and leaf uptake, so we actually see this trade-off where carbon actually isn't the main driving factor of the social benefits and values until about year 35. Before that, it's really focusing on the uptake of health. And again, these are just kind of examples, so there really aren't labels, but essentially this is the carbon, this is going to be your particulate matter, the social benefits of taking up particulate matter. And this table shows a few different case studies that we did with it. So if we don't include ecosystems at all, that's kind of our standard annualized privatized cost for this industry. We looked at if we just include the physical uptake. So if we take away the social benefits part, and we only look at the trade-off of 1 ton of particulate matter, whether it's taken up by trees versus the technological alternative, which would be like a baghouse filter. But only looking at it as a physical property, so trees or technology to take 1 ton. That's kind of when we just call it a physical uptake, and then when we include the health impacts, we kind of get these other, an increased valuation of the ecosystem services. And then we also just did an extra one that constrained the spatial amount, the land area, while we include the value of health benefits. to that which we will have the physical uptake, and I'll explain why in the next slide. But essentially, I think the main takeaway that we've got from this is that when we add valuated health benefits or social benefits to the objective function, we were able to get kind of an 84% increase in just these social benefits, while only really seeing a 6% increase to private costs. And so that was a trade-off that we found very interesting in terms of it's a pretty negligible increase. I mean, at that scale, I would say obviously it's still a lot of money, but in the scheme of things seems negligible to the really added benefit, whether or not it's paid for by one industry or maybe even a whole area of industries and maybe involving a lot of other stakeholders. And then the comparison between the physical uptake and the health impacts when we constrain them to the same amount of land area we'll talk about next, in which case the conclusion really is that spatial arrangements matter. If we include health impacts, we see, so this is actually the city of Cincinnati in both figures. We're not actually including a lot of land area there because we're assuming that there's not a lot of available land, so there's a constraint based on how urbanized this particular area is. But you can see if we only focus on physical uptake, we can get these kind of scattered areas of where it's just kind of based on the plume. This is actually the dominant direction of the plume or the downwind direction of the area. So related to this industry, there's a dominant area here, but it's also based on land cover, how much land is available to change. That leads to kind of the concentration changes. And then once we are able to include health impacts, we see the role that population actually plays in it. So again, just the fact that we're able to do this in a spatial matter, that we get significant differences. And just between these two, one thing that's interesting is that it's the same amount of carbon sequestered and the same total area of land use changes. But within this, we actually see that the health impacts on the left basically increased by about 50% to the right in terms of averted mortalities. And between the two cases, it's 90% from left to right and about a 23% increase in overall social benefits. And just the reminder that those social benefits include both the mitigated climate and health impacts. So we'll wrap up this section, in which case we're just going to talk quickly through the insights and then the general takeaways of this type of work. So the first is we shouldn't really just focus on planting trees to only offset carbon. What we really should focus on is planting trees with an intention to address other things and the co-benefits of trees, such as public health and any other co-services that we identify as particularly valuable to the community, including ecosystem co-benefits, drastically increases the perceived value of land-based solutions. It more accurately accounts for all the different functions of nature, so it gives a little bit more livelihood to the planet. And then it includes a societal perspective on ecological benefits, which is able to expand kind of the realm of possibility for the metrics we use in design, being able to focus more on well-being, justice, sustainability, rather than just really focusing at the private perspective of an industry in design. General takeaways for this kind of work is how we define our systems and system boundaries is important. Unintended consequences can occur when we're not thoughtful about what we neglect. So again, going back to why we expand our system boundary. A reminder that people, land, technology, they're all connected and each play a role in pursuing sustainability. And then finally, holistic solutions require holistic approaches. So collaboration and interdisciplinary study is essential in providing useful solutions to these grand problems. And I just wanted to give a quick list of some of the future directions we're looking at in the lab. And the first is just that key component of moving forward, which will be focusing on really building community. Having community partners where we can test any of these computational things and go back to those main questions we started about, that I started with, which is around data-driven storytelling, advancing methods for decision makers, and making sure that our computational design really centers around community. So again, those community partnerships will be challenging our approaches, and ideally we get to ask them, is this useful? And that will help direct the directions of future research. We talked about kind of the ecological network analysis and topological network design, specifically working with communities in rural areas for applications in electricity and water distribution. going back to that hierarchical design approach for techno-ecological and social systems, where we're just finding systematically how do we include feedback from people into the way that we approach our, either feedback into our optimization programs, or how do we take that and turn it into metrics or things that actually start to really tune into what people are asking of us. And then multi-scale in integrated assessment modeling, so specifically looking at connecting global climate and economic changes to the local impacts for tribal nations. So that's one project I've been working with my own tribe back home. And then also developing an AI approach essentially for identifying where useful knowledge exchanges can be had. So looking at tagging conditions of various environments over time in the context of climate change and identifying where places and communities may overlap. So may have useful knowledge systems for where they are now versus where they may go, and identify where people might have already experienced what their particular environment is about to experience. So that was one thing we talked about kind of at a global level when we were talking about kind of the exchange of indigenous knowledge. And so I'll wrap up so we have time for questions, and just want to thank, a lot of this work was done at Ohio State while I was there, which was through the NSF and a graduate research fellowship, and then also a collaborative centers grant. And I'm excited to be back here at Cornell and the BEE department, and also thank you to the American Indian Indigenous Studies program. So in my language we say a or thank you, and I'll look forward to any questions.
Yeah. What is I've seen your last slide, like what would be your approach for rural and rural applications for electricity and water distribution?
Yeah, so what we're looking at is for specifically areas that don't already have electric grids. The main question they're really asking is, do we develop a microgrid? Do we implement technologies so it's just one solar panel on one house and that's the source? Or is there value in implementing it into a larger grid? So like in the US, like really we're on 2, 3 grid systems, but some of these smaller communities that it's not reaching, the question is it worth investing in like very rural areas? So our reservations, the northeast desert of Arizona, it's pretty spread out. I don't know a better way to say it. But it's, when do we make the decision to include houses into the broader network? When can we create a microgrid? And specifically, how does that impact our costs, but also the reliability, the redundancy, and basically what happens when interruptions happen? Is that something that even matters to the community, that if they haven't lived with electricity, does the 2-day blackout really change their life or not? Where if that happened here, all of us would be scrambling and panicking. So questions like that, but really looking at costs versus trade-offs of reliability.
So would you be looking at would you be applying the same model which you applied for assessing the human health effects on this as well? Because for example, if there's hardly any source of electricity in those rural areas, so it would have an impact on the human health as well, since the hospitals might not function as much as possible. So would you be focusing on that as well?
Yes and no. It would depend on what those power sources are, right? So if it is something like, if it is, localized solar specifically, because that case is in Arizona, solar is a pretty good option. We're not really going to be looking at the health impacts of air pollutants. But if we look at, maybe there's a centralized coal plant or power plant that they've decided, or a natural gas spot, then we can start implementing those types of metrics. I think what becomes a little bit more valuable, depending on the technologies, can be basically community acceptance, community understanding of that, and what happens when things fail, right? So who's building it, who's maintaining it. So I think that's where actually technological education and adaptability becomes a more interesting metric, but obviously if we find that health impacts play a role, then that's something we'd like to include. Or either way.
So any considerations of including in the analysis a case of policy reversal, meaning right now the policy is set to set the goal by a certain year, and there's a budget and there's the status quo. But every 4 to 8 years we may have policy reversal. What I'm saying is if there is a way that this can be included, not to do nothing, but policy reversal, meaning the goal, if you pick up 4 years gap of something opposite, after 4 years, the cost to meet your original goal, now it's budget-wise is unattainable. I'm saying if there is a way that you can communicate that in the analysis to show the gravity of embedding the policy in the form of a law instead of executive order, or something.
Yeah, I see. So basically, how do we design with robustness to policy changes or even terms? It's an interesting thing. It requires definitely a lot more political or policy analyzing than I do at this point. It would be interesting, though, in terms of how do we react. If we can turn policy and policy reversals into constraints within if we can turn that into a mathematical constraint, it's very simple and straightforward to include in the optimization programs. The challenge will be identifying where those, analyzing the policy to identify how to turn that into a constraint. I would say it's definitely possible, and what's also interesting about a lot of this work that we've been talked about when we're considering policy is not like at a policy scale is you couldn't just rely on land anyway at this point because the EPA doesn't have a good way of crediting that. So if you're already over, if you have to first stay within the policy limits that's already set by the EPA. So when we talk about this trade-off between technology and ecology, it's kind of a toy problem at this point because unless policy begins to start accepting ecological systems as a valid way of meeting these policy limits and things like that, then we're still working within a different bounds that we haven't really explored as much yet.
So I follow up.
Sure.
Is there a setting right now that geographically you can plant trees in the state of Ohio, or you can plant those trees more efficiently or less cost to plant them, say, somewhere in the East Coast, but we still share the hemisphere? Is there any laws for prohibiting to do that or maximizing the effect? Right?
I would say we're at a point where carbon markets are so underdeveloped we don't even know what the laws are. But it's a huge conversation, right? Say there's a company that's doing a lot of work here in the U.S. Say they just go and buy an acre in the rainforest. How does that impact like the Amazon? How does that impact global trade markets, tax credits, redundancy? That's one of the biggest things, and they took at the UN level. I'll say they took about 6-7 years, if not way more than that, where it really just focused on carbon markets, just to agree if they should exist or not. Now they're still at the point where, all right, what are all these things that we've been talking about that we need to remember as they're trying to really put together guidelines, specifically international policy. Hopefully that develops faster within domestic policy. Ideally it should, but who knows? Do you have a question too?
Yeah, probably quick comment. So the last we talked about this geospatially disaggregated in the control model. So based on that, did you have any insights about what would be a good, not necessarily optimal, what would be a good granularity for climate policies and actions?
Yeah, that's a great question. That's not something we've studied a ton. What I will say, what we've talked about in the even other things moving forward, we kind of multi-scale modeling. How do we make a decision at a wide scale? Can we pick the best county that needs help in addressing maybe a health disparity issue, and then from there can we model that county to find even another hot spot where it seems promising to plant for the carbon. It depends, because when it comes down to land management, you're not buying probably 100 acres at a time and planting it all at once. Identifying a spot where you could do that, and maybe then there's other constraints of even availability of land use and things like that. Maybe there's other constraints that won't really impact the granularity at that point because there will already be policy maps or local issues that you can just kind of follow, but you've identified that as a hotspot. But I wouldn't say I have an answer of what's the right resolution. I think it just depends on what scale you have resources to implement. So.
Yeah, I think that's a very good point. One thing we experience is really, when we go to the very detailed, refined granularity, while you can model those things more accurately, because climate change, all this greenhouse gas, this is really a regional challenge. And when we do these things, actually, for example, reducing 1 ton of greenhouse gas emission can be less costly this area rather than that area. So when you try to control for every area at a very fine scale, to give up opportunities for cross-grid kind of offsetting or kind of taking advantage or arbitrage of those opportunities. So I suspect that kind of if the granularity is too fine, actually the cost of climate action could be higher than at larger scale measures.
Yeah, I completely agree, and I think it also kind of goes back to the idea of like why collaboration is needed too, because there are people that do. I mean, I believe Max Zhang in civil mechanical engineering, does that high level. Where should we plant trees, or where should we make address health inequities based on just alongside the road, right? How do we make sure that air pollution from just road travel is adequately addressed? Where we're looking at like countywide, regional, city planning levels, and that you really do need both, because it's like you mentioned, it's going to be hard to ever get to a point where you have very adequate. We can't put that scale of resolution across an entire county or even city, but you can start to kind of identify hotspots is the term I like to use, but those different ways to interact across scales. I think that's really what's important.
Thank you.
Yeah, thank you.
George has a question.
Oh yeah, you got some text questions
Okay.
in the chat.
We have one more in the room, and then I'll look at these. I see, some in the chat as well. Al, George, if you can either put it in the chat or we can unmute you in a second.
No, I'm unmuted. Can you hear me?
Okay, we'll do this first. Yeah, we can hear you.
Oh, okay, good. So first of all, outstanding talk and perspective. That's a very needed way of looking at the problem. The question is, I've been working with Ithaca Green New Deal, which is basically the city of Ithaca trying to go carbon neutral by 2030.
Sure.
And one of the things that's very clear to us is that the societal input is extremely heterogeneous. We have landlords, we have people who are renting, we have communities that are less advantaged than others, et cetera, scattered around. I'm curious about what each of them have different perceived values, perceived effects on their health and the environment, societal, et cetera. And do you have any ideas about how to work with that? I mean, it seems to be you need social sciences and people from the humanities involved in this, but I thought you probably have thought about this and might have some comments for us.
Yeah, that's definitely a tough one, which is how do we basically include all of these disagreements as a social system of how we should move forward. And yeah, a lot of that goes to how we value things and what are the values of a community. And I think the best way I would say is really try to find if there is any place they do agree, right? So if it's a lot of people who might disagree on the value of carbon might agree that saving a life or preventing like lung disease in a county might be something that's a noble goal. So I think the more we think about this as a co-benefit framework, we can try to identify things that maybe aren't politicized, or maybe things that people aren't wishy-washy and disagreeing on, and find benefits that we can actually all focus and agree that that's something good for the community. And then we focus on that as being how we pitch it, how we have these projects, but then we also are mapping out all the other benefits that we have that address these other issues. So it could be a city that's really not focused on climate, addressing public health, things like that, and that's how we now just get to measure those benefits without really that being the focus. So hopefully that gives a little insight.
Thank you.
And then we have one in the room, and then I see one more in the chat.
Yeah, I was wondering, for when you take into account the social costs and benefits, it was sort of done economically, so it was single objective. So what are the scenarios where you can't do that, where there are social benefits that can't really just be made into an economic money value? Or even if you can do it, like what are the downsides of just having everything in terms of dollars?
Yeah, so for those online, the question was, what happens when you can't turn a social benefit into a value, a dollar value, or turn it into an economic objective? I think aesthetic is one thing that we're never going to be able to put, a dollar on. It goes back to probably more where how do we include it into a community value? So something like aesthetic, where we know that if we just let grass grow and kind of wild out and just maybe be a foot tall in some areas, we have wild native grasses, that's going to actually be probably the healthier ecosystem, take up more carbon. But when we think about how we even campuses, right, we're going to want really nice mowed lawns so when parents come through it looks great, and it's what looks better on a picture than what looks better for function is a big thing. I think that's something we'll never include a dollar value into because we can't, but I think it goes back to how do we include that as a co-value of a community. How do we turn that into a discussion? How do we split where maybe there's areas where we should keep that value because of people making decisions or the community response. But we won't be able to do everything. I think that's very true. And the only other way to really include it in terms of the optimization program, even if it's not a economic dollar as a single objective, you could turn it into a multi-objective where maybe it was we take a survey of how many people smiled because of the grass was cut, right? Now we can optimize for smiles if we can figure out what functions are related to that. So there are ways you would most likely just be turned into a multi-objective where we have objectives in different units, but we'd have to figure out how to quantify it still. And then I'll just look at the one in the chat, and then I think we could probably wrap up. The last one I see is if we connect issues of decarbonization benefits with increased access to electricity. As an example, could we also couple the idea of paying the landowners for sequestration or increased forest cover? So yeah, Michael, this goes into the idea of payment for ecosystem services. That's kind of a big thing that's kind of going on. Specifically, I think, and knowing that you live in Ohio, because it is a very relevant issue because we have so much farmland and agricultural land. So that is something that they're looking at is people who, especially big landowners like farmers, what are other ways they can maybe even have a more consistent income if there is a bad harvest or a bad winter? Are there other ways that they can use that land to create income? That's very much being discussed. I think it's part of the carbon market discussion and policy discussion, both globally and domestically and probably at a state level. But I think it is much, it's a valuable conversation to have in terms of other co-benefits as well. It could be even, wetland management, going back to Ohio farmers and the nitrogen runoff that's led to the eutrophication of Lake Erie. So that is something where controlled wetlands could actually be used to mitigate the amount of nitrogen that actually runs off into these bigger fisheries. That could be something that we should be paying for, or the state should be paying for, to help address a whole different issue. So it doesn't have to just focus around carbon and carbon offsets. And so I think it's still discussions to have, and if anyone's interested specifically in that example of eutrophication and nitrogen runoff, we have a paper on that from an old colleague as well. So, but I believe that's it at this point. Thank you to everyone who's online. Oh, there's one more. I see a question from Susanna. I can answer that since I'm still here as well. But I'll let people in the room trickle out.
Great. I just had a quick question. So I had been reading previously about people saying like a PNR, like the point of no return as far as global climate change and all that. And essentially between the projects and research you have completed and looked at, what do you feel is the priority as far as tackling a specific type of realm of research and like really implement change immediately so that can decrease the time frame that we have to the PNR essentially?
Yeah, that's an interesting question. I mean, the biggest thing was actually figuring out, I would say it's more in the communications than it is the research. It's getting people to act. It's less what's the next paper we write versus what's going to turn the next dollar towards something that matters. I would say in terms of the ecosystem services to focus on, that would probably be carbon at this point, knowing the kind of the urgency of climate change. So that would be kind of where I would direct focus, but I think having a framework of how to do it, if we're going to put our money in, is there better ways to do it than just let's plant as many trees as we can? Can we have a way to do it a little bit more intentionally?
Got it. Thank you.
Yeah, thank you.
This is Jerry Stenger. Will you tolerate one more question?
Yeah, I can do that.
I want to really compliment you on doing such a great job of putting reasonable numbers on what are often vague concepts. As opposed to saying we should think about these things, you really did. The question I had was, I was a little uncomfortable when you had the 3 boxes for technology, ecosystems, and society with a lot of distance between them, because it seems to me, in many cases, technology and society sort of go together. The technology you have affects how people relate to each other and what activities they have to have. And certainly if you think about rural communities, they're often very tied to their ecosystem, whether it's fish or plowing or forestry. And what challenge does it give you if you want to recognize that society, technology, and ecosystem are not sort of separate circles that interact a little bit? Oh, Al's with me on that one.
So, can you go back? What was the question?
Well, do you want to expand on the idea that those boxes are not far away? They're actually very much overlapping. If you pick a different technology, in some sense, you may have to have a different society, or vice versa.
Sure. Yeah, and I think that goes back to kind of the beginning, where what we're trying to do is figure out how to adequately model those relationships between technology, ecology, society, whether or not we see them as separate or just, even just different parts of a bigger system. But how we define those relationships is, I would say, very difficult, but agreed. That's also why when we talk about things like climate, why there's so much deep uncertainty is it's not just being able to model the ecosystems and the environment and rising sea levels, it's how will we respond, what will happen in the future, what technological changes will we have in advancements by then, our behaviors, is it something that we take seriously, is it something that people in their own daily lives address in a different way than we have? So it becomes less than just, let's see how we can transform these economic sectors to, how do I live my daily life? And so I completely agree that that's all extremely intertwined, and I think that's, addressing these issues is finding better ways to kind of incorporate all those solutions, but it also, like I mentioned at the beginning, it invites a bunch of challenges. A lot of different researchers will be needed to kind of identify and quantify those different relationships.
I think as the host, it's now.
I can just add a comment to Jerry's question and your answer.
Sure.
I think we all agree with that. But I think the way to look at this is that initially people look at these problems just technologically, and then you have everything with externalities. The step you're having is you have a different externality with some coupling. Okay,
Mm-hmm.
the real. Eventually, you have to look at this thing as one unit without just simplified coupling between them. And I don't know how to do this, but I don't think anybody really does. But I'm just saying, I think that's more of a transdisciplinary rather than interdisciplinary approach that is really needed. And that's why I mentioned the social sciences and humanities to get essentially the input from society in a more nuanced way rather than just assuming there's some positive and negative opinions on a certain topic. It's more complicated. But anyhow, I agree with Jerry. This is a really great talk.
I'm as the host, I'm going to cut you off now.
Well, thank you.
Because everybody's left and we've got Michael trapped up here at the front. So. Thanks, everybody.
But, yeah, I appreciate everyone. Thank you so much.
Thank you.
Yeah, thanks for staying on.
All right, no problem. All right, bye.